breeding applications, and then we will discuss some limitations and opportunities. So the outline of this presentation is very quickly, now we have less time, I'm gonna talk about the breeder's labor. So to understand a little more about the motivation, why we are doing these things. And then I'm gonna introduce very quickly two key concepts that we consider in plant breeding: genomic selection and genotype by environment interaction. Then we will review very quickly some of the prediction methods and models that were already implemented or developed under parametric approach, and then we will try to understand how these were evolved or how these are connected with the AI methods that we have nowadays, or some of them actually. Then I'm going to show some of the results that we can find in the literature, why these models can be good but haven't shown the real potential. And then I'm going to show some of the new models that we are trying to develop, where we are trying to connect both types, the best, I would say, of both approaches, from AI and from the parametric models. And then with a sparse classification with multi-type data problem. And then at the end, we will have probably this evening time for the questions. Okay, quickly, what's the motivation? What moves us to work in this area? As we know, we live in a world is growing, so we have around 10 billion people expected to be in 2050. Currently, we are around 8 billion people. So one of the biggest challenges of the humanity is to ensure the current and future food supply chains of a growing population. And this is not the only problem. The other problem is that we live in a world that is facing more often and more extreme environmental variations. In this case, the breeders have a main role to develop improved varieties. And we can think of improved varieties of having varieties that yield more, or they are more resistant to biotic and abiotic stresses, etc. So very quickly, this is the conventional breeding pipeline. You know for sure better than I do how it works. At the beginning, we need to screen a very large number of genotypes to be able to, I'm going to show my point. Okay, sorry. To be able to select the best ones and reduce the number of genotypes to be screened. On the other side, we increase the number of locations where we are testing these genotypes. In a way, at the very end, when we are developing a commercial line, very few genotypes are tested in a large number of environmental conditions or environments. In a way that we are lucky, we will be able to select between 3 to 5 lines that will be commercialized as elite varieties. One of the interesting things, at least in common crops like soybean, soybean pretty much, is that the genetics that we have at the beginning of the breeding pipeline is exactly the same the genetics that we have at the end of the breeding pipeline. In a way that if we were able to develop a method that could help us to find what the reduced set of genotypes that we should consider to advance in the breeding pipeline at the very early stages, we will be able to save the most important resource, time. So also money, also resources, land, water, etc. Okay, some of the inconveniences of this conventional breeding pipeline is that we have limited resources, availability, land, and it's expensive, time consuming, so we cannot wait 8 years to, we have to for now, but it would be great not to have to wait 8 years to release a variety. However, in our favor, we have some factors that can help us. We have better sequencing technologies. We can characterize genotypes in a better way. We have better ways to characterize environments using environmental conditions. Also, we have the help now from automated systems that can help us to capture a wide range of phenotypes using high-throughput phenotyping methods. And also, we have improved prediction models. We have the parametric and the non-parametric sides. We have artificial intelligence, we have machine learning, deep learning, FDR, boosting, and hybrid methods that can be combined. Can be obtained by the combination of these two. Okay, why we are talking about these things? Because we are trying to save time, pretty much, in order to select the genotypes to be advanced. So, as we know, many of the important traits are complex in the sense they are affected by a large number of small gene effects, and also these gene effects are affected by the environmental conditions that they face in fields. In a way, these two factors interact in many complex ways. Suppose that we have a set of genotypes tested under normal conditions, but let's say that at the same time or later on, this same set of genotypes is tested in challenging environmental conditions. It might be the case that some of these genotypes will be able to make it through these challenging environmental conditions. So the idea is trying to develop methods that can help us to anticipate what could be the set of genotypes to use when we can experience negative environmental conditions or challenging environmental conditions. For this, we have tools like genomic prediction. There's an no, it's not an emerging methodology anymore. It has been tested in many different crops and have shown that actually some genetic improvements or genetic improvements can be obtained. So the concept is very easy to understand. Initially, we need phenotypic and genomic data to train the models, and then we can use this information to evaluate test candidates using their market profiles in a way that we can provide these predicted values as surrogates of phenotypes to the breeders, and the breeders in theory might want to look at the values in order to help with the selection process. Again, the breeders are interested in developing genotypes that perform others in a wide set of environmental conditions, and for the reason they have to test genotypes in multiple environments. However, in many cases, we experience this type of behavior where, let's say in this example, we have 3 genotypes tested in 2 environmental conditions, where genotype B has a low performance in a low environment, a high performance in a high environmental value. The opposite for genotype C, and genotype A is constant. If the breeder wants to select the best genotype across the environmental conditions, they won't be able to find the best one in this case. Let's face it, breeders deal with thousands of genotypes tested in multiple environments, not just 2. So in those cases, this problem becomes even more difficult. So we have 3 different options to solve this problem. If we want to say solve, we can ignore the fact that we have this effect. This is called genotype environment interaction, and we can just select using the means across environments. We can reduce it by selecting for local adaptation, but might not be the most desirable outcome. And then we can exploit it by trying to borrow information between genotypes tested in different environments in a way that we can try to find those genotypes that are stable across environments. Okay, now let's have a quick review of the prediction methods and models. So far we have, in one side, parametric models. You can say Bayesian or penalized methods. We have non-parametric methods, what we call hybrid methods. And we found that some of these are generalizations of existing methods, but considering hyperparameters in the case of AI methods. So very briefly, we have 2 big branches: parametric, where we find penalized and Bayesian methods; non-parametric, where we have kernels, AI, machine learning, deep learning, etc. And some hybrid methods that are based on kernels, where pretty much we are trying to simulate these complex methods from AI. No? Let's say that we are trying to explain the performance of genotypes based on a wide set of data types. Oh, sorry. Can you see my screen still? Okay, there. Okay, so we can use a function where we can pretty much relate all of these different sources of variability to explain the phenotypes. Genetics, could be pedigree, could be markers, RNA-seq, and other layers of the omics for genomics, weather, soil, etc. So let's check very quickly the parametric methods. We have that we can explain the performance of one genotype using a linear combination between markers and marker effects, and we can have assumptions in 2 different ways. We can consider penalized regression methods, where we have a trade-off between model complexity and model goodness of fit. So where we are trying to find the argument that minimize this sum Estimate the error between predicted and observed values plus a penalty, a condition on the effect of the covariates. We find the solution for this case for the R block, assuming normality, is the x prime x plus lambda, the penalty parameter in this case, inverse x prime, and the residuals around 0. So we call this R block model. On the other hand, we have Bayesian regressions where we use a sum a prior distribution for the effect of the covariates, and we find that the posterior mode is somehow equivalent or very similar in the shape to the solution for the R block. Some of the problems that we find in this case is that we have to invert these matrices. They are high dimensional in many cases, and we have to deal with that. So in this case, this lambda parameter is equivalent to somehow to the ratio of these variance components is helping us to break this singularity by adding some bias in the diagonal of this x prime x matrix. We will see later how this is related with AI. We have alternative parametrizations, and the STAR model that we are using in many cases is called G-block model, where we are just replacing this linear combination by genomic effect, and we stock all of the genomic effects, and we compute by the moments of this vector. So the covariance of G, the stock vector of genomic effects, equal to x beta, has a covariance given by x prime sigma square beta, and expected value of 0, in a way that this characterization of the characterization of this random term is a normal distribution, x prime sigma square beta, where G is equal to x prime divided by P. In this case, this is the kinship metric, so covariance structure is going to help us to borrow information between pairs of genotypes, because each entry describes the genomic similarities between pairs of individuals. We find that if we solve this problem, assuming normality for the effect of the markers, we end up with a solution for the posterior mode of the genomic effects given by the identity plus lambda times G inverse minus 1 by the vector of residuals around 0. In this case, we are getting directly the combination. So one of the important things here is that we, again, have here embedded this lambda parameter. And now we are dealing with the inversion of matrices of order n by n. So this is less challenging than matrices of order p by p, assuming that p is greater than n. Doing research in the same sense, we developed many years ago already a model that allows to include interactions between genotypes and environmental factors via covariance functions. So we developed this reaction norm model that helped to improve predictability. And we consider this interaction component between markers and environmental covariates. And we found that when we characterize this component, the covariance structure is equivalent to the product between the covariance given for kinship metric based on markers of pedigree and the metrics constructed with the environmental values. In that way, this is just the cell-by-cell product between these two covariance structures. Now we just characterize this as a random term that follows a normal distribution centered in 0 and covariance given by G Hadamard product omega. Now, regarding the artificial intelligence methods, or what sometimes we call non-parametric, we can think of some of these methods as generalized versions of parametric models. We have linear regressions, we have kernels. In the sense of, in the case of the linear regressions or linear methods, we have the main difference is that these require the optimization of the hyperparameters, while the parametric methods use Bayesian or likelihood methods. We have a prior, for example, for Bayesian. On the other hand, the corresponding AI methods use cross-validation studies to optimize the election of this shrinkage parameter, the regularization parameter, this lambda value. Regarding the covariance structure based on kernels, we have that these describe similarities between pairs of observations or individuals at the level of the genomics, environments, phenomics, etc. So we can think of elaborated relationships at the level of the covariates that can be modeled considering kernels. We can have distance, functions, transformations, etc. In a way that the ultimate goal is to improve the correlation or the correlation between pairs of entries or between entries for each one of the different model terms. It could be their genomics, environmics, phenomics, etc. And also we have another set of models, neural networks, with these are generalization. It is a generalization of linear methods where we have embedded multiple regressions. We have latent variables, activation functions, hidden layers, hyperparameters, etc. So here again, when we are thinking about the alternative ways to understand these AI implementations, we have penalized regressions and the Bayesian regressions. And we said that here we can get the lambda parameter given the penalized regressions, or we can obtain also the Bayesian, using the Bayesian approach, indirectly this regularization parameter as the ratio between the variance components of the error and the variance components of the effect of the markers. So we have prior distributions for each one of these ones. So we can get directly or semi-directly this lambda value. So on the other side, we can find lambda using cross-validation studies. So if we are thinking in some similar kind of AI modeling. In those cases, we have it requires to divide the population in 3 non-overlapped data sets, where we use one for compute the marker effects or the effect of the different factors. We have another training set that we are trying to optimize this lambda value for a given decay parameter. So that is fixed, is a hyperparameter in this case. On the other side, we have these are just parameters. Here, these are hyperparameters, meaning those are given. And then once we have the beta values, lambda values, we apply this to the testing set in a way that we can evaluate predictability of the model. Now, regarding the machine learning methods, so some of the first thing that I did when I started working in this area was to understand or to learn what are the AI methods. So we found that if you Google this, it says that it is the theory and development of computer system able to perform tasks that normally requires human intelligence, such as visual perception, speech recognition, decision making, and translation between languages. So, but what about machine learning and derived methods? So this is a graphical representation of the AI methods, and embedded in this, we have the machine learning methods. Embedded in this, the neural nets, and embedded in this, we have more and more specific methods. We have deep learning. So this, all of the categories, or all of the different fashion of these methods that we can find in artificial intelligence. So for machine learning, we have the use and development of computer systems that are able to learn. I think that's the key part, and adapt without following explicit instructions by using algorithms and statistical models to analyze and draw inference from patterns in data. So let's learn a little more about these kernel methods. So if we think of why the response can be explained by a function of the data that we might have, the covariates. In this case, let's say that we have genomic data. We can use this data to map individuals based on similarities. So by transforming X using a function K of X. So the first step is the first step consists of computing this transformation. And this is very useful for capturing complex patterns that we cannot identify or are difficult for us to propose. What are those? Sometimes we might have some feelings of what could be those, but when we don't have any idea, we can use these methods, especially when the number of covariates P surpass by far the number of data points available for model fitting. So P greater than N. Also captures different types of interactions. We have epistatics, G by G, G by E, and epistasis by environment. So here we have a what are the different type of kernels that we might find in the implementations. We have linear kernels. We have the what is the solution or what the covariance that we are considering in this case is alpha times x prime, and the parameters to optimize alpha, the trace of this divided by n. So we know this model is known as gblob. We have a similar parameterization for finding the epistatic kernel. I just use the Hadamard product between these two matrices. So we already discovered this. And this is the way how we find the parameter we are interested. Gaussian, based on RBF, they use the applying a transformation to the metric, where this metric is a sometimes, I mean, in this case, is a Euclidean distance between the genomic information between pairs of individuals squared, and we just apply this transformation, and we optimize the parameter by using the median. And these are particular cases of RKH, reproducing kernel Hilbert spaces, or support vector regression. Also, we have arcosine. They use a transformation. I want to explain the whole transformation in this case, which is based on sines and cosines to modify the axis. In this case, we optimize by finding the right parameter for theta. So this can be think of a deep kernel of a hybrid method that tries to mimic the deep learning methods from machine learning. So this is the way how we find the solution. Many times we can get the solution at once, especially when we have very large number of parameters. So if we think of the linear predictor y equal to g plus e, we have the k is too big to factorize. The solution, I mean, the factorization is null. I mean, we don't have a factorization, and the solution is equivalent to the normal equations, where we have k plus lambda I, g equal to k y. So g is equal to g. Is how we get the prediction of the breeding value. If we can find the inversion, it's going to be very easy just to get the inversion of this k matrix. It's not full rank, it is full rank, for example, or it's not that complicated. So we can just think of getting this, the inverse of this, and again, g is equal to g. Or if we can perform the spectral decomposition, it could be eigenvalue decomposition. For example, we can factorize these metrics in 3 matrices, 2 associated with loadings or eigenvectors, and 1 associated with eigenvalues. And we obtain the solution of G as a transformation of U times A. And also using the Cholesky decomposition, where we can factorize this using the upper triangular matrices. They are very easy to get the inverse, because we just rely on the diagonal of the matrix. And then we obtain the solution by getting G equal to L, the product of the triangular matrix, by A. Okay, now let's talk about the artificial intelligence methods based on deep learning. So we saw the support vector machine, random forest. Deep learning is a set of methods for machine learning for GS, for other implementations also. A deep learning is a subset of the machine learning, which is essentially a neural network with 3 or more layers, and these neural networks attempt to simulate the behavior of the human brain, albeit far from matching its ability for now. Allowing to learn, that's the key part there, from the large amount of data. So here we have that we can characterize the inputs. We can put here all of the different data types of the information that we have. It could be genomics, phenomics, weather, etc. And we can think of neurons as linear combinations of all these inputs. We also have embedded some kind of activation function that based on some criteria, we can activate whether the neuron is important to contribute to explain the variability or not, and then we can keep moving to the next layer, and so on. So we have, in these cases, different parameters that we might be interested in optimize, and each one of the layers we have bias, we have weights, etc. And we have to we have embedded the different regressions. At the end, we use a linear combination of the neurons derived from the last layer to predict the performance of the unobserved genotypes. In this case, we have the machine learning. It have, as we said, learnable structures. We have weights and bias, but also we have structures that are not something that where we can, how the method can learn. So these are the hyperparameters. And in this case, we have neurons, hidden layers, number of layers, type of activation function, etc. So since the hyperparameters are provided for the user, many possible scenarios or combinations should be considered to find the best strategy initially. This is a small example. Suppose that we have 8 choices for the number of layers. Could be 3, 4, 5, 6, 9, 10. So there is not a rule that we can find the optimum number of layers before doing the analysis. 3 choices for the number of neurons per layer. It could be 4, 5, 6. 4 choices for activation function to decide whether a neuron has relevant information or not. So the total number of potential scenarios is 3 to the 3, 3 to the 4, 3 to the 5, 3 to the 6, 3 to the 7, 3 to the 8, 3 to the 9, and 3 to the 10 times 4 activation functions. This is a total of 88,560 times 4, around 350,000 combinations. The scenarios that we might consider to find the optimum for one rep, because every single time that we run these methods, we have a random component embedded. So here we can take advantage of the high throughput computing facilities using thousands of cores simultaneously. So we already developed in this paper some methodology, or one methodology that can help us to develop complex pipelines in a very easy way, assemble modulus for conducting predictions using parallel computing for millions of combinations. So tuning process of hyperparameters consider 3 different non-overlapped data sets. We need first one for training the set, for training the learnable parameters, another not overlapped for tuning the hyperparameters, and finally one for testing or validate whether the strategy that we are following with the estimated parameters and the hyperparameters is helping or not in the terms of predictability. So using similar ideas to what we have here, like dividing the 3 different, dividing the whole population in 3 different data types, we developed some models where we are trying to combine the best of the AI, the pure B AI, and the best of conventional prediction methods. So we develop an implementation that we can actually improve classification compared with machine learning methods. So we will see this at the end. So these are some of the results available in the literature. So we have the Montesinos et al. Is one of the pioneers in the advancing these models using AI. They tested 9 models, the models using 9 different data sets, and they compare versus the model that we proposed many years ago in terms of predictability. So these authors found that many cases when interactions were not included in the model, in this case in the right panel, deep learning outperformed conventional GPLOP models, because as we said before, it has embedded somehow this or can find these complex relationships. However, when the interaction was included in both methods, deep learning and GBLOB using the rational model, the extended GBLOB model outperformed deep learning in most of the cases, in this case in the left panel. So we have here in red the results from the deep learning, in gray the results from the GBLOB. So here is very clear that deep learning is better, here is not that clear. So these results highlight, in this case, the importance of using these AI implementations in order to be able to capture these complex relationships. However, when we are able to formally include these parameters in the model, we don't see that much improvements compared with the conventional AI methods. Also, we recently published in this paper a study where we try to use, or we try to compare the different 4 different methods: GBLOB, Gaussian kernel, deep learning, and arc-cosine kernel, with and without interaction to predict yield performance. We study the case of predicting sparse testing, so genotypes in already genotypes in already environments. So this is what we call CV2. We have in orange the G-block model and in gray the deep learning method. So for a direct comparison. So we have the when we don't include the main effect, so the interaction between genotypes and environments, deep learning does a good job in some of the environments, but not in others. However, when we include these interactions, it's clear that the methods based on covariance structures outperform the deep learning method. On the other side, we have the predicting new genotypes that we didn't observe in any environments using the main effect method only, or models. We have better results using deep learning. However, when we consider the interaction components, the improvements are not that clear. Actually, the parametric, semi-parametric, or hybrid methods do a better job in this case. So pretty much these results highlight the need of developing new improved prediction models under conventional and AI approaches for improving predictability. So here we have there are some advantages of the machine learning methods. Support vector machine and random forest. They are very easy to implement, require very few parameters to be tuned, little time to provide complete predictions. Deep learning is very powerful, capturing complex patterns in the data, like interactions. Also supports raw data, so there is no need to process the data. We have integration of several sources of information, omics, such as pedigree, genomic data, environmental data, metabolomics, microbiomics, phenomics, proteomics, transcriptomics, etc. The downside is that we don't have a strong theoretical support, warranted only local minimums, computationally are demanding, requires tuning of hyperparameters. As we saw, we can end up with millions of combinations. Different omics are treated at some point as the same data type, and no interpretable resources might be obtained. So these are these methods are also known as black boxes, which return outputs for a given input. So take-home message is these are very good methods for performing predictions, but we cannot blindly adopt them. Somebody already said in a few publications that these methods are not a panacea. We still have to develop in-house implementations. So now I'm going to switch gears. I'm going to talk a project that we were working for quite long already, and it's almost about to be published, the integration of multi-omics for improving phenotype prediction in the binary case. So we tried, again, as we said before, try to take the best of each one of the implementations, AI and parametric methods. So we have the nowadays sophisticated and automated system allow the collection of different types of data with potential applications in plant breeding. We have high throughput sequence and phenotyping, drone, greenhouse data, pictures, etc. The integration of these multiple omics is increasing expectations to improve predictability of current models. However, the large number of covariates also poses challenges for bringing this information in the model. In plant breeding applications, the main problem when combining two data types like SNPs and secondary traits is that the genomic covariates will outcompete the phenotypic covariates to explain the performance of the plant. So you have millions of markers and information on 20 secondary traits, whatever is there goes away with this large number of covariates when you treat them as the same type of variable. So we have data classification problems. We have the several traits can be categorized based on continuous measures. I mean, soybean, we have lodging and shattering, it has categories 1 to 5, draw and salinity tolerance for rice, for example. So the simplest case corresponds to the binary outcomes where we have only two categories, zeros and ones. In this case, we try to leverage the concept of sparsity that is linked to the identification of major genes controlling trait performance. Again, out a large number of genomic variants, a small number is highly correlated with the response. Also, usually secondary traits have a lot of information with respect to the main trait of interest, like, for example, yield. We can use canopy coverage, lodging, shattering, etc. In this study, our goal was to develop a method that performs conventional Bayesian and machine learning classifiers. Pretty much we tried to blend both of these. So we have Bayesian, lasso, A, B, We have random forex, support vector machine, FDA, etc. So we consider the binary case. Suppose that we have a large set of microscopic variables P, in this case, U, the metrics of markets, and a reduced set of macroscopic variables Q of this, W, the secondary traits. In principle, we can combine, or we can think of combining both sets in one big matrix and treat them as the same type of covariate. Apply the commonly used variable selection methods, lasso, Bayesian lasso, or machine learning classifiers. In your case, we propose a method that is based on the ideas of Huang and Turnbull, where we use an iterative method for selection shrinkage of variables in highly sparse linear regressions. We use the same principle for the selection of variables. We distinguish the nature of both sets. So here we gave first priority to the set of macroscopic variables, the secondary traits, and then conditionally on this, we selected those variables in the microscopic set, so the molecular markers. We call this one-pass method. So this method, how it works is we start selecting for the secondary traits at the point where we cannot increase the likelihood more, and we break the loop. If we have 20 secondary traits, probably we selected 10, and those were enough to explain why. And after that, we started selecting from the set of markers. And then we add a threshold optimization to find the group's memberships, so zeros or one, pretty much, based on the evidence of when is the point where we are going to send predicted values to the group of the ones or the group of the zeros. So we also add another novelty here. We regress the macro variables using the marker data, just one at a time, because we believe that some of the information that is from the secondary trait that is not on the genomic data can be recovered via the residuals. For this, we consider the elastic nets for the regression, the lasso, and the scat. And then we merge these residuals together with this set of genomic covariates. So again, potentially this will help to recover information not in U, in the macro variable, in the genomic data, but is just in W through the residuals. It's the same principle for selecting variables, but distinguishing the nature of each set. So we are giving priority to the set of macroscopic variables, and then conditionally we select those from the set of micro variables. So we are going to present results using two real data sets. So we have simulations, but we don't like simulations too much. So we have a data set of maize with 277 genotypes, and the main response was tillerin, presence or absence of tillerin, the extra branches here. There are some maize breeders that believe that when you have extra branches, reduce the yield potential. Other breeders say that it doesn't matter. So we just were interested in analyze this data set. So we have information on 20 macro variables or secondary traits, 4 methods to include the macro variables, raw, lasso, scat, and elastic net for the residuals, 5,000 molecular markers, total of 5,020 markers for 20 replicates for composing, training, and testing set. This is the way how we conduct the cross-validation. We use 77 genotypes for testing the model, and for training, we have 200 genotypes. And we divide for one-pass method in this way. We have 120 to get the estimate the coefficients, and 80 to estimate the threshold. And finally, we use this to classify the outcome that we're interested. For machine learning, we use directly the 200 genotypes, and we let the machine learning to optimize in their own way to predict the remaining 77 genotypes. It's the same idea for tuning hyperparameters in deep learning. In this case, we have a given decay parameter for running this optimization. So we evaluate the classification error, so the lowest, the best. So in this case, we have in the left panel the results using the AI implementation, machine learning. On the right side, we have those derived from the methods that we propose. As you can see here, for the different methods that we propose, especially for raw, and for elastic net, we have a lower classification error compared with the machine learning methods. So the classification error was significantly reduced by using the proposed methods. However, further developers should be considered to add more omics and multiple categories. Also, we have similar results for the case of soybean, where we try to assign genotypes to different groups, zeros and ones, based on 20 covariates, secondary traits, and markers. In this case, again, we see this clearly, the results with the method we propose are clearly superior when we have different proportions of zeros and ones in the population. We have 50-50. We got classification errors of 0.3 compared with 0.4 with the AI methods. 65-35, we have some cases we have around 0.27 compared with the 0.35-36 with the AI methods. 75-25%, we can say that they are tied at somehow, but still a little bit of improvement compared with the method that we propose compared with the AI methods. And finally, with the 85-15, I think they are just bailing out the outcome. So we are pretty much getting the same results. So currently, we already extend this methodology to consider the inclusion of 3 different data types: secondary traits, weather, and SNP data. We use a subset of the 3,000 lines of chickpea tested in net environment, 14 million markers, 9 secondary traits, 900 weather covariates. So we have that extended one-pass method returning a classification error only 50%, while the support vector machine and random forest was 30%. So the take-home message is that it's important to treat the different omics differently depending on the nature and number of variants. Adding information of all omics without the previous consideration will not allow us to fully leverage in the prediction classification problems. And the AI methods can be significantly improving by differentiation the different omics, instead adding all this in a bold fashion. With this, I don't have anything else to show. Thank you so much for the opportunity again. Obrigado, and I think I'm open for questions. Probably at the end.